So when you write define, you want this on paper, right? A calculator.
What?
Like
What?
like this is define integral. You want like on paper, like where? Maybe where this.
Yeah. Yeah. Definite. Doesn't say define. It says definite.
I can't English.
Yeah. So all right. So first, before we jump into Carter's question, I just want to remind you of the fundamental theorem, part 1. So part 1 of the fundamental theorem says you've got this function f of x, it's continuous on some interval a, b, and then we make this other function we're going to call capital F of x, and it's defined to be the definite integral from a to x of the original function f. Because we're using x as an endpoint, we can't use it inside 2. We have to do a public dummy variable, and that's what t stands for there. And the other day, I called, instead of calling this capital F, I called it a, because it's an accumulator function or an area function. Okay, because it adds stuff up is basically what it does. Because this is just a fancy sum. The reason at first I don't use capital F is because a lot of people in math aren't case sensitive. But I think at this point in your math careers, you've learned that capital A is sometimes different than lowercase a, and capital F is different than lowercase f. So we got to be case sensitive here. So that's the setup for the fundamental theorem. But what the fundamental theorem says is that the derivative of this accumulator function, this sum function, is the original function f, which we call the boundary function, right? If we look at it geometrically, it's the top curve. So I'm going to restate that one more time, and that's going to kind of get to Carter's question. So little f is big F prime. So what I can do is I can go rewrite my definition there and say that going back to the original statement here, capital F of x on its own is the integral from a to x of capital F prime of t dt. And this gets to that idea I mentioned the other day that was discovered a couple hundred years ago, a few hundred years ago, even though calculus has been around in its various forms for thousands of years, that the integral and the derivative cancel each other out. They undo each other. Okay? And it goes in both directions. Which means this says take the integral of the derivative. Okay? What about taking the derivative of the integral? It works that way too. Okay? So like with multiplication and division, it doesn't matter which happens first, they cancel each other out. Same thing with the derivative in the integral. There's a slight catch called the chain rule, which we'll see here in a sec, but that's the basic idea. Okay? They're opposite operations, essentially. All right. So now over to Carter's question. By the way, this statement, where's my pens? They're missing as usual. Why does that one happen lately? I think it happens more in the winter. It's the cold, yeah. So the fundamental theorem of calculus is this right here, part 1 is that. I need you guys to memorize that, because on the test, I'm going to ask you, what is the fundamental theorem of calculus, part 1? And you're going to write that down.
Just those 3 lines.
Those 3 lines right
If
there.
x continues in AB.
Yeah. If little f is some continuous function on an interval AB, then we make this accumulator, this sum function, based on the definite integral. If we make that assignment there, then the derivative of the area function happens to be the boundary function. Right? That's the geometric interpretation of words. But I need you guys to know the symbolic interpretation too. All right. So it's in the book too. Take a look at the book in a minute for some of the next stuff we're going to do. So now I'm going to take a look at Carter's problem. Let's see. Section 3, number 3. So here we have the derivative of an integral. And copy that. So it says use part 1 of the fundamental theorem. What we got here. Where's my screenshot button? So a couple of different ways to think about this. You could just do it as you see it. So order of operations here is to evaluate that definite integral first, and we can use antiderivatives. So this isn't the way they wanted me to do it though, because they said use part one. I'm going to jump to part two for a sec. So what's an antiderivative here?
1 divided by 7 t to the 7th.
Yeah, so we increase the power by 1, then divide by it. So 2 to the 7th over 7, or 1/7 times, whichever your preference. And then I'm ignoring the derivative for a second. We were asked to evaluate this from x to 19. So that's going to give me 19 to the 7th over 7 minus x to the 7th over 7. Right? We evaluate the upper boundary, subtract, evaluate the lower boundary. So again, I said this the other day, my process for taking definite integrals, first thing I do is I write down the antiderivative, then I put a pair of square brackets around it, write the boundaries back in, and then I set up my subtraction. Okay. And we'll do that a bunch of times today. Now, I haven't finished this problem because I haven't applied which part? I haven't taken the derivative yet, right? So I have to take the derivative of all of this stuff. So if I were going to take the derivative with respect to x of that new stuff I have, well, 19 to the 7th over 7 is just a constant, right? Then I have a minus, which is like -1, so I'm going to get a negative. The derivative of x to the 7th is 7 times x to the 6th. And this is divided by 7, which means I get a negative x to the 6th. And so Carter was kind of wondering, where the hell does that negative come from? So here's one way it comes from based on the fundamental theorem part 2. Next, I'll do it the way they asked me to do it. Everybody see what I'm doing here? All right, so I'm just applying, I'm ignoring their instructions, and I'm doing the fundamental theorem part 2. Now I'm going to go back and do it fundamental theorem part 1 now. So bring this to the screen. New page. Okay, fundamental theorem part 1 says that if you have the integral from some number a to x of some derivative, then the answer is f of x, whatever function you took the derivative of. So the integral and the derivative cancel each other out, essentially. That's what the fundamental, this is a slightly different version of the fundamental theorem part 1. So in other words, I have the integral from a to x of the derivative with respect to t of capital F of t dt equals capital F of x. Okay, how is this different from my problem? Well, the x and the 19 are switched. Okay. So if I want them to go the other way, instead of walking forward on the number line, I'm now walking backwards. How do you describe walking backwards? Negative, yeah. So I can rewrite this as the derivative with respect to x, pull a negative out, and then this can become the integral from 19 to x, t to the 6 dt. And the order that you do these derivatives sort of does, the derivative versus the integral sort of doesn't matter, as long as that's just an x up there, not something like an x squared or sine of x. That gets funkier, we'll look at that later. So according to the fundamental theorem, then this part right here should just be x to the 6th. But because I changed the direction of the integration, I have a negative in there. Okay. So the fundamental theorem part 1 is super powerful, but it's subtle and it can do all kinds of things, and some of the things it can do are pretty subtle.
You do that for any integral, flip the bounds, just make the whole negative.
Yes. Yeah, because you just change direction on the number. So it's like y is positive going up, negative going down. The fundamental theorem, because of the way we build Riemann sums, the definite integral, because of the way we build Riemann sums, is always assuming x goes in a positive direction. If you try to make it go the other way, you just introduced a multiple of -1. If you try to go backwards. Does that help a little?
Yes.
Okay. And I'm going to do this again when I'm going to do a problem where I toss something up in the air and try to track it. A similar thing happens. It's kind of cool. All right, so let me see. Other things, number 12 area, and then around number 25. So number 12. Okay, and then 13. Okay, so these involve the fundamental theorem. Okay. Screenshots, new page. What did I do? My screen go. He is acting funny. All right, so they give me this function that's defined as an integral. Now, this is too complicated for us to come up with an antiderivative. And it turns out that happens a lot in math, that we have this weird function that came from this situation, and the function's so complicated, we can't come up with an antiderivative. So you can use definite integrals to define new kinds of functions, and that's the only way they exist. So like, think about how weird the cosine was when you first came across it. Does anyone remember thinking, this is a bizarre thing, cos of x, what the hell, right? But now you're used to it, right? So this, like the cosine was an amazingly weird new function that you got used to. We can now create new kinds of functions based on an integral. And that's the only way to state them sometimes. There isn't an antiderivative version of it sometimes. Okay. I don't know if there may be an antiderivative for this. It would take me a while to figure that out, but it doesn't matter, it turns out. Because what am I asked for here? I'm asked to find a local max. Well, that's a Calc 1 problem, right? To do that, I have to take a derivative. So I need to know what is f prime of x. Well, that means I just need to take the derivative with respect to x of this integral thing. Well, what does the fundamental theorem say when you take the derivative of such an integral? They cancel each other out. So that means the derivative of f has to be just that inner function there, written with x's. So it's just x squared minus 16 over 1 plus cosine squared of x. So that's f. Just get rid of the integral. Put x's in. That's what fundamental theorem part 1 tells us. Now here comes the hard part. A local max is a little bit more work. Two ways a local max can occur. One way is by setting equal to 0 and see what x values give me 0. Then I have to test to see if they're a max or a min. Right? The other thing is if the denominator is undefined, that can sometimes lead to a critical point too. In this case, with the cosine, I'm pretty sure it's not going to. So the only time this is going to be equal to 0 is if the numerator is equal to 0. So that means x squared minus 16 equals 0, which x would be plus or minus 4. Now those are just critical numbers. I don't know if they're maxes or mins. Anybody remember the tests? We had two kinds of tests to figure that out. What's that?
You plug into original equation, see if it's.
Well, we could make a number line and plug numbers on each side of these into the derivative to see if it's increasing and when it's increasing and decreasing. The other thing is to take the second derivative and plug 4 and negative 4 directly into the second derivative. Okay. Now, thinking about the quotient rule, I don't know if I want to do that. Right. So we're going to do the first derivative test for increasing and decreasing. So the first derivative test, you just say, okay, there's -4, there's 4 over there. Oops. I need to pick some test values. So my favorite test value when I can use it is 0 if it's applicable, and then numbers on each side there. So maybe over here I might put -5, and over here I might put 5. And all I care about is what's the sign of f of x. And actually, I think I'm going to pick different numbers. Let me see. Well, I guess I'll just stick with 5. 0 is easy. Let's do that one. So if I plug 0 in, I get -16 in the numerator. Now, oh, the denominator is kind of interesting. Yeah, so the denominator here is 1 plus cosine squared of x. And normally the cosine of x sits between -1 and 1, right? If I square the cosine, what happens?
It just changes.
Then it's going to be between 1 and 0. And if I add 1 to that, then I'm between 1 and 2. So looking at this thing right here, this thing is always between 1 and 2. Yeah. That's kind of nice, which means it's always positive. Okay. So when I plug in 0, what's the sign of this thing right here? Nope. Try again. If I plug in 0, right, I'm going to get a -16 in the top. I'm going to get a positive number in the bottom, so it's going to be negative. So f prime of 0 is less than 0, which means this function is decreasing through there. If I go back here and I were to plug in 5 or -5, either one squared is 25. The numerator is going to be positive. Denominator is always positive. So sign analysis tells me that over here, f prime is greater than 0, function's increasing. Over here, f prime is greater than 0, function is increasing. So a local max occurs at -4. That's what we established based on that. This problem is more of a review of Calc 1. That little trick about the fundamental theorem part 1. All right, so x is -4. Ooh. All right, and so these other problems are pretty similar. You just have to think about what's happening with this inner function here. That ends up being the derivative, which is what you need to figure out where local maxes happen. 14, fundamental theorem to find the area under the curve. Was that one I was asked about? I can't remember. We're going to do one like that anyway in a minute. 25. Okie doke. Evaluate the definite integral. New page. New page. Come on. There you go. All right. So this involves the fundamental theorem part 2, which says, can you find an antiderivative? Let's see. What function would I take the derivative of to get the sign? Cosine, right? But the derivative of cosine is really the negative sign. Okay. So in an antiderivative, I'm going to put a square bracket, is going to be related to the negative cosine. Now, there's a 4t here, so I'm going to put the 4t here. So sometimes finding antiderivatives is a matter of like guessing and checking. If you take the derivative of what I've written here, let's see, derivative of the cosine is the negative sign, so the negatives cancel, that's good. But what happens about the 4t? The chain rule would be multiplied by a 4. We're missing a 4 out here. I wish there were a 4 right there. Can I just multiply a 4 in there and be done with it? That's going to make the answer 4 times what it should be. Yeah, so one trick would be, I want a 4 to be there, so to compensate, I'm going to multiply by 1/4 outside. What's 1/4 times 4? 1, they cancel out, right? So that's one trick. So what that means is I'm going to have a 1/4 or divide by 4 over there for this to work. So now double checking. If I take the derivative of this thing I've just created here, derivative of cosine is negative sine, negatives cancel. Derivative of 4t is 4. 4 divided by 4 is 1. This works. Okay. So sometimes finding antiderivatives is kind of a trial and error. That's the antiderivative. Now I can plug in the boundaries and see where it leads me. So that's going to give me negative cosine of 4 times pi over 4. All over 4. Then careful, we subtract, and I have a negative. Cosine of pi is -1.
Yeah.
So that's going to be -1 times 1 is 1/4 from that. Cosine of 0 is 1. So I'm going to have minus a negative, so plus another 4th. So it looks like this is going to be 1/4 and 1/4 is 2/4 or 1/2.
So I did that by U substitution and got the same.
Yeah, so I haven't covered U substitution yet. I'm going to do that tomorrow. But since you brought it up, I might as well do a preview now. So this is another cool trick. So integral from 0 to pi over 4 of the sine of 4t dt. So the 4t is troublesome here. So we can get rid of it with what's called a change of variables or a substitution. I'm going to pick a new variable called u, and then let u equal 4t. Then what you do is you take the derivative of u. The derivative of u with respect to t is just 4.
Yeah.
Okay. And then I'm going to write it in differential form. When we talked about differentials a while ago, so I could say du equals 4 dt. Now, I have a dt up here, but not a 4 dt, so I could take that 4 over to the other side. That's going to give me 1/4 du would equal dt. And so now I'm ready to do that substitution with those two things. And I recorded a video yesterday for tomorrow that I'll make sure everybody gets, where I do a whole bunch of these. And I show when it works and when it doesn't. So then I can rewrite this actually as the integral of the sines of u, and then dt is replaced by a 1/4 du. Two ways to go from here. These boundaries I wrote in black. What was the variable up there? Those are the values for t, so I'm not going to write them directly here. If I want to put values here, I would have to plug those numbers for t in here to figure out what u should be. Okay, so for example, if t is 0, what would u be?
0.
Yeah. And if t is equal to pi over 4, what would u be? Just pi. So here, if I were going to rewrite boundaries, I have to recalculate. And there'll be more on that tomorrow. So if that looks really weird to you, don't worry about it right now. There'll be more of that tomorrow and the next day. So that would be an alternative approach. And if you follow through with that, you'll get the same answer we just got. All right. So let's see, what do I want to do next? The next thing I wanted to do is, remember on day one, we talked about antiderivatives? And to do that, I asked you, we wrote a list of like a ton of derivatives that we could remember. So we're just going to kind of do that backwards today. We're going to make a list of antiderivatives. And the types of things we're going to call here, these are what are called indefinite integrals. Indefinite. So we're going to build a partial indefinite integral table by thinking about antiderivatives. So if we were to integrate, something like 3 with respect to x, what's a possible antiderivative for the 3? 3x, yeah, because the derivative of 3x would be 3. Now there could have been some constant there. So indefinite integrals means you don't know what the boundaries are, which means you have to adjust for that constant. If it's a definite integral, you don't have to worry about the constant. What if we had the x? What function has a derivative of x? Yeah, x squared, but then, yeah, because if we take the derivative, the 2 would come down, so we have to compensate by putting the 2 underneath. And then plus c. In general, we have a reverse power rule for integrals. So what if I needed the antiderivative of x to the n with respect to x? What's that going to look like?
X to the n plus 1 divided by n plus 1.
Yeah, increase the power by 1 and then divide by it. And it could be a constant. So those are the ones we need to kind of build polynomials. It turns out this works whether n is a whole number or a fraction. It's kind of cool. So let's see. Suppose I wanted an antiderivative for the square root of x. Well, first I would rewrite that as x to the 1/2. And then I can use this rule right here, which says do what? Almost, we add 1 to the power, so that's going to give me x to the 1/2 plus 1, which is 3/2. And then I have to divide by 3/2. What if you were dying for that to be a square root? Well, we could turn it into a square root. So one possibility here is right, the 2 in the denominator means square root, the 3 means the 3rd power. So I could rewrite this as the square root of x cubed over 3/2. You could multiply by 2/3 if you want. I don't think we really need a formula for the square root of x because I think it's easier just to rewrite it as a power. That's an antiderivative for square root of x. Other functions we played with before, antiderivative for the cosine of x would be what? Almost. Yeah, it'd just be the sine of x because the derivative of the sine is the positive cosine. Yeah, it's the other way that gives us trouble. If we try to take the antiderivative of the sine of x, that's where the negative comes in. Tangent, you're going to have to hold off on until tomorrow or Friday. I'll prove that one later. It's just not as straightforward. But what if I had the secant squared? Yeah, that would be tangent as the answer. The antiderivative for the tangents are a wee bit more complicated. And I'll show that tomorrow in a video, or Friday on a video. Antiderivative of secant of x times the tangent of x. Remember what function had that derivative? No. Arcs are a whole other story. What is it? Thought I heard someone say. Secant. Yeah, this is the secant. Yeah, so based on all the derivatives we've done, we know a lot of antiderivatives. Okay, we could fill up several pages if we kept going. I'm just going to write 3 more. So what about the antiderivative of 1 over the square root of 1 minus x squared? What function had that derivative?
Is that
Arc?
arc cosine?
Nope.
Oh, sine.
Arc sine. Yeah. Arc cosine would be a negative up there. Yeah, this one is the arc sine. Or the inverse sine. Oops. Plus c. Okay, and there's a whole bunch of ones related to the arc functions. I'm not going to go over all of them. I'm just reminding you that you do know a lot of antiderivatives right now. Antiderivative of e to the x?
E to the x.
E to the x. I love that one. Yeah. Beautiful. We're going to have to hold off on the natural log. That's a tough one. We'll get that next week. But what about 1 over x? ln, yeah, it's the natural log. Yeah, because the derivative of the natural log is x. Now, there is a slight catch here in the way I wrote it. I have a problem. 1 over x, I can plug in positive and negative numbers, but the natural log of x only accepts positive numbers. So technically, if I write it this way, oops, eraser, there should be, can I get my eraser? There should be an absolute value around the x here. Or we have to restrict x to only be greater than 0. So that's a bit of a complication. And we're going to keep building lists of antiderivatives because we're going to need them for other functions. So if you check out the textbook, let's go into the 1.3 for now. Under the table of contents. So in 1.4, there's a link to a partial list, which is just a little bigger than the one I just made right now. But if you look away at the bottom of the table of contents, there's a table of integrals. And even this is a partial list. You could fill a book, a very large book, with integral tables. So look at, there's just a ton of them.
Is that in the book or separate files?
What's that?
Is that in the book or?
This is in the book too, yeah. So in the print book, there's an appendix at the end. So in book 2, this is an appendix A. In book 1, I can't remember which appendix in, but it's in one of the appendices. Yeah. And you can go to the internet and search integral tables, and you'll find a ton of websites that list anywhere from 10 to 1,000 or more possible integrals depending on the function. And so there's a section in the book where we try to evaluate integrals based on either tables or a computer program. So we'll play with that later. All right, next topic. So Fundamental Theorem Part 1 and 2 combined. Give us another idea called the net change theorem. And one version of the net change theorem is that if you integrate from some value A to some value B, the derivative of some function, then you just get to evaluate that function's antiderivative, f, at B, and then take away at A. So this is a combination of putting what part 1 says together with what part 2 says. So we're going to apply that to a velocity problem. There's a couple of similar problems in the homework. So this is section 1.4 we're going over. So we're going to take this object that has a velocity, and let's see what I pick. 20 minus 9.8 times t. So interpretation of this particular problem, the 20 would be an initial velocity of 20 meters per second. So I threw something up in the air, straight up in the air at 20 meters per second, and the negative 9.8 is gravity trying to pull it back down. Would be the interpretation here. This right here is related to the force due to gravity. And what I can do is based on that rate of change there, so this right here, v, is the derivative of the height, the rate of change of height. Okay, so change in time of whatever my height function is. So I can find what's called the net displacement. Which would be net change in distance of this thing if I integrate from one spot to another. So I'm going to start off going from 0 to 2. And so if I integrate h prime of t dt, that will tell me in the interval from 0 to 2, where is it compared to where it started. Now, it doesn't tell me the total distance traveled. That's another thing. Remember I mentioned the other day, integrals tell us net change. They don't tell us, or net area, they don't tell us total area, because they could be positives and negatives. So in this case, I just need to find an antiderivative for 20 minus 9.8t. In order to solve this, and then I can evaluate it. And that's all the net change theorem says. Okay. What's an antiderivative for 20 minus 9.8t? It would be 20t for the 20. And then minus, the t becomes what? T squared over 2. So I'm going to have 9.8 over 2 times t squared from 0 to 2. So what's that going to be? If I actually carry that out, I plug in my 2, and I get 20 times 2. Half of 9.8, I believe, is 4.9 times 2 squared. Minus, and then I do that again with the 0. Now in this case, 20 times 0 is 0. 0 squared is still 0. But do yourself a favor and write that out just to confirm to yourself you really do get zeros there. Because it turns out we end up plugging in the 0 a lot when we're evaluating these things, and we get into the bad habit of assuming it's always 0, but it's not always going to be. Depends on the problem. So I need to whip out a calculator for this, because I can't do that in my head. Guys are whipping out calculators. Let's see what we get together. So 40 minus 4.9 times 4 is 20.4. Okay. Okay, so I'm going to have you do that one more time. Interpretation, again, based on my beginning saying that was 20 meters per second. Integrating with respect to t is multiplying by seconds. 2 seconds elapsed here, right? And so this must be meters then, because I took meters per second, multiplied by seconds through the integral. The result is meters. So in 2 seconds, it started at 0 meters. It's now at 20.4 meters. So next, you're going to repeat the same thing, but now I want the net displacement from 0 to 4 seconds of this same thing, 20 minus 9.8t. Do that one, see what you got.
Find displacement.
What's that?
Find displacement.
We're finding the displacement, yeah. So we're just exactly as we see it, we're just doing it.
I'm taking the derivative, the one we just found.
We need to, well, in order to evaluate this integral, I need an antiderivative, which is the same as before. So that's going to be 20t minus 4.9 t squared. But now I'm evaluating from 0 to 4. That's the only difference here. Which is going to give me 20 times 4 minus 4.9 times 4 squared minus parentheses. I still get 0 minus 0 there. So what does this come out to be?
I got 1.6.
1.6 is what I got too. Okay, so the question is, how can the displacement over 2 seconds be greater than the displacement over 4 seconds? Yeah, it's net displacement, right? So this thing went up for a while, and then it started to go down, and the net means we had some cancellation of movement here because it went up and back down. So what this tells us is that 4 seconds after it was launched, it's now 1.6 meters higher than when it started. That's all this tells us. This is just net change. Total change is different. Do you remember what I said about total change before? Total change is you're integrating from wherever to wherever. To get rid of any cancellations, you basically have to take the absolute value of the function. Okay, that's a bit of a problem because definition of absolute value of some object, well, it's that object if that object happens to be greater than or equal to 0, but it's the opposite of that object if that object happens to be less than 0. So that means we have to find every place this function changes sign between here and here. And then we have to break it into multiple integrals. There's no other way to do it. Okay? And I mentioned that the other day. Net area is easy. Integrate, plug in, done. Total area, way harder. We have to do some analysis in between. So analysis time. So because of the definition of absolute value, I have to look at my v function, which happened to be that derivative of height, which was 20 minus 9.8 t, and I got to figure out when it's greater than 0 and when it's less than 0. Okay, so there's 2 ways at least to do that. One way is to say, well, the negative parts are of most concern to me because that's when I have to flip it. So just solve the equation, the inequality, when is this thing less than 0? So I'm going to subtract 20 over. Negative 9.8 t is less than negative 20. But then I have to divide by a negative, so what happens? Flip the inequality. So t is going to be greater than negative divided by a negative is a positive, whatever this number is, 20 over 9.8. We go with the calculator, approximately what is 20 over 9.8?
2.0408.
2.04, okay. 2.04. Yeah. So notice earlier I went to 2, it hadn't started to drop yet. So I got the full distance it traveled up to 2 seconds. After, a little bit after 2 seconds, all of a sudden it starts to fall, and we get some cancellation of height because it's dropping down again. So we have to break this into 2 integrals now. Because if you were to graph the velocity function, what you would see is it starts up here at 20, and then it drops down in a straight line here, and it hits right there exactly at that value. So from 0 to that number, I can just integrate no problem. But on the other side, I got to take the opposite so I can get it to go that way instead. So I can get the positive version of that negative area down there. Okay? So all I have to do is break it into multiple integrals. So I'll show you how I do that. So I can't, if I want total area, I have technically I'm starting with the integral from 0 to 4 of the absolute value of 20 minus 9.8t.
So that would just be 0 to.
So to get the to deal with the absolute value, I have to say, okay, this is now two different functions, a piecewise function. The first piece goes from 0 to 20 over 9.8, exactly. And I'm going to choose to use the exact version of the number. And there, I don't have to worry about absolute value. And then what I want to do is I want to add on to that the next part. The next part goes from 20 over 9.8 up to 4. But there, I want the opposite of this sucker. And the opposite of this sucker would be negative 20 plus 9.8t. So I have to do those in two different parts. Okay? I have to measure its, in this case, positive movement, and then separately I measure its negative movement. I ignore that it's negative. Essentially, that's what this lets me do, and put it all together to get a total amount of movement. Went up for a while. Now, just say how far did it go down, put those two together, and get a total distance traveled.
Does it matter if it's negative? Does negative stuff have to go between? You can put outside in?
You could put the negative out here into a subtraction of all of that. Yeah, so you need to choose some way that you're going to not screw up the signs. So I usually find for me, if I just put that negative in there right away, I'm less likely to screw up the signs than if I put the negative out here instead. Okay. All right. And then we make that calculation. I'm not going to worry about that right now. The hard part was figuring out where to break it, which means you basically have to find its zeros. Any regions it's negative, you've got to integrate separate from where it's positive. And you're going to take the opposite of that. And we are about out of time for fun with math today. So I'm going to stop there. In section 1.4, section 1.4 is a lot like section 1.3 in that we're applying the fundamental theorem in this manner. And the other thing about the fundamental theorem it says is, hey, find all the antiderivatives you can and just use them. Okay, so there'll be a bunch of problems like the problems in 1.3. With more variety. And then so I'm going to record, let's see, I'm going to record 2 more videos. I'm going to record me doing a couple of homework problems from section 1.4, more stuff like this. And then I already recorded 20 minutes on substitution, which is section 1.5. I'm going to record another about a 20-minute video on using substitution. Okay. So, and again, I won't be here. You guys are welcome to come here and study together or hang out in the lab, or you could watch videos and study together. It's up to you, because I have that interview thing I got to go to Thursday and Friday. So I'll be pre-recording the next 2 days in 3 15 to 20-minute videos. All right.